welcome guys. So this is a short video. I just want to talk about a quick application of this BHT algorithms. So from Gravers. So this is like the Gravers algorithms, but with a little bit non-trivial change. Okay, so the settings that we have f from let's say from 1 to 2 to n, right? So we have n, which have a set. Let's say a, we have the number of the set has n elements, and f from 1 to n. Okay, and it needs to output, and we are assume that. So we assume that so f is 2 to 1. And n is even. So we are exactly say that n is even and f is 2 to 1. That means there's always a exists x not equal to y such that f of x equal to f of y. So the task is to find such pair. So basically you need to find two element x and y such that f of x equals to f of y. And the only things you can do is just query this f, right? So you can just pick up, you can just pick up I, and store this f of I. And the idea is that you need to find such pair. Okay. So let's see if you working classically, right? So the idea is that if you're working classically, then the deterministic, and all you can do is just you have a box, right? And then you collect. So basically you can just collect f1, f0, and f1 and f2, right? And until you find some I such that fi from ij, which is not the same, such as fi equals fj. Okay, so classically, I think it at least need like n, right? You like need to n divided by 2. So for deterministic, you need to at least n divided by 2 plus r, right? So and this can be seen things as suppose that so let's make a let's say f1. Oh, sorry, not f. So f1 and f. So let's assume that from 1 to n minus 2. And then n plus 2, 1 plus 2, n divided by 2 add 1, and n divided by 2 add 2 up to n. They are all so we assume that these two, if we assume these two are the same, and these two are the same, and these two are the same, and then you start from here, then you at least need n divided by 2 plus 1 to find such pair. So this is the deterministic answer. Okay. So if you but secondly, if you assume that your algorithm can do randomly, then you can, by the birth-stack paradox, then you can prove you can at least do a square root of n. So the idea is that how about quantum? Okay. So the idea is that for the quantum, that we can prove that it only needs 1/3 n to the point is basically like n to a 0.333. Okay, and the proof is very interesting. So naively you may think unique Gravers algorithm can only take up a square root of n just like randomly. But idea is that the answer is no, right? So idea is that you just pick the first 1/3 as your queries. So you first take the 1/3 square n to the 1/3 power as the queries, and store them to make a table, right? So you first take a. So there are two cases. The first case is that you find such pair. Then you success, right? But there's some probabilities that you do not find such pair. Right, so how many? If you success that you take n 1/3 to find such pair, okay. But if you do not success, that means you have a table basically contains like let's say f1, f2, and up to fn 1 or 3, and for the rest, n divided by 2, n to the 2/3, you take a square root Grover speed up. So you just use the Grover search to take this. And your x your function, your indicator function is that if you pick any one of them and it's the same as this, then you just stop. So you only need take n to the 2/3 square roots Grover search. So totally you need to n to the power 1/3, 1/3, and 2/3. Take a square root. So total you just need this. So it's better than a classical. So the idea, let me just explain the idea again. So you just pick the first n to the 1/3 power as your queries, and then you store them to make a table. So there are two cases. The first case here, you can find such pair. So it's success. If you do not find such pair, then for the rest n to the 2/3 power, you just take any of it and see whether it's already in the lookup table, right? So by the Grover's algorithm, you only take the square root of n to the 2/3. So you only need n to the 1/3 and add n to the 1/3. So total is, for the complexity, is n to the 1/3. So this is better than the randomly square root of n, and that is n divided by 2. Sorry, I changed the small lowercase n to a capital case for uppercase n, right? But ideally, this is ideal. Okay, now this is a famous BHT algorithms. So if you just Google Wikipedia and search for BHT algorithms, then you can show this is you can see the same argument. Okay, so this is the first, I think this first non-trivial Grover search, Grover's type of algorithm, which is really interesting. And I will see you guys in the next videos.